Hello guys, welcome to this video. This is the November 2023 paper 2, question 2. In this question we are given a light source that enters some materials, and this diagram shows the way the light rays are reflecting and refracting. And the student labeled 2 points, B and A. So this is point B and this is point A. And the question says that we have an error at both of these points. And the first part of the question wants us to determine these two errors. So first of all, let's discuss what the error could be at point A. So if we look in our data booklet, we can see the formula for Snell's law is that n1 over n2 is equal to sine of theta 2 over the sine of theta 1, where these angles are always measured from the normal of the plane. What this means is that if we have some light ray coming here in, then we draw normal. This normal is just a perpendicular line to the surface, and we always want to measure the angle in between our ray and the normal of the plane. So if this is like the incident ray, let's say this is the refracted ray, then again we want to look at the angle between the normal, and so these are the two angles, and we usually label the first material number 1 and the second material number 2. So 1 is just where the light is coming from. So if we look at this question, we see that at point A, we are traveling from plastic to water. So we can say that this is material 1 and this is material 2. Now from this we can also see the refractive indices of the two materials. Refractive indices pretty much just tell us how much light slows down in this specific material compared to a vacuum. So in a vacuum, the speed of light is 3 times 10 to the 8 meters per second, and these ratio numbers just tell us how the speed of light compares in these materials. But if we look, we can see that N1 will be plastic. I'll just write plastic here, over N2, which is going to be water. So water is going to be 1.6 over 1.33. So we can clearly see that this is going to be a number that's larger than 1. But for this equation to hold true, which it does, it must be that the sine of theta 2 over the sine of theta 1 must equal this 1.6 over 1.33, which means that this is also going to be larger than 1. But this means that theta 2 must be larger than theta 1. Otherwise, the sine of these angles will not be larger than 1. And what this means is that the angle of refraction should be larger than the angle of incidence. And if we observe what these angles are here, we can clearly see that the incident angle here is demonstrated as being larger than the refracted angle. So that's not really possible here if we're traveling from a higher to a lower refractive index. So what we could say is that when we are traveling from between a phase where the first material has a higher refractive index than the second material, then we must have the case that the incident rays angle must be smaller than the refracted rays angle. This can also be thought of by the fact that if we are traveling to a less dense medium, then the ray must bend away from the normal, and the angle has to be larger as the light is speeding up in this material. So here this must be the case, but in the diagram this is not the case. So in this diagram, theta 2 is represented as smaller than theta 1. So the refracted is smaller than the incident, and this should be the other way. Yes. And then we want to do the same analysis for light at the water-oil interface, or position B. Now, if we look at this situation, what we see here, let me just get rid of this. If we look at that place, then what we see is that we actually have no refracted rays. So there are no rays entering the oil medium. All the rays are hitting this boundary and refracting back. This is what we call total internal reflection. Total internal reflection, as everything is being reflected. Now there's a very special situation that has to hold for this to be possible, which is that first of all, we see that the refracted ray has an angle of 90 degrees when it is on the boundary. So if we draw the normal over here, then if this incident ray would be a little bit larger, at a larger angle, then right at the critical angle, we say the ray will not be reflected or refracted, it will just be on the surface. And if we increase our incident ray's angle, then this arrow will move from the boundary back into our material. But for this case, we see that the second angle here, so theta 2, is equal to 90 degrees. Now, if we look back in our equation we used in the first question, we will see that the n1 over n2 will be sine theta 2, which is sine of 90, as this must be the angle for total internal reflection to occur at the critical angle. Then this sine of theta 1, or we could say the critical angle, as this is the angle, as I said, where there is no reflection or refraction, is just on the boundary. Then that's what we call the critical angle, and then we'll see that this is 1 over the sine of this critical angle. Now if we rearrange for this critical angle, we will see that this is n2 over n1, and then we can take the arc sine of both sides so that we can solve for the angle. Now what's important to know is that an arc sine is just the inverse function of the sine. So it pretty much just means that we give a number, like for example, if we have a sine graph like this, and then we say we want the arc sine of 1, so this is 1, then what this function will return is at what x value we are. So let's say 90 degrees. And so this is just what it means. But if we see the the sine function is always between 1 and minus 1. So if we would plug in here like a number like 2, for example, that would be asking like, at what x value is the sine of x equal to 2? Well, that's not really possible because the sine function never takes the value of 2. So this must mean that the argument, what's inside of here, must be smaller than or equal to 1. Otherwise, this function is undefined. If you try and plug in something in your calculator like arc sine of 5, it will give you an error as that doesn't exist. So from this we see, for this to be less than 1, we can say that the n1 must be larger than or equal to n2. Now, if we look back at our question here, n1 is 1.33 and n2 is 1.47. And we can obviously see that this is larger than 1.33. So this is not true. This is not true here. Because in our example, n1 is smaller than n2. And so in this case, we couldn't even have total internal reflection. So the student should have definitely drawn some refracted ray as well, not only a reflected ray. So that is the error here. So we could say according to the diagram, total internal reflection occurs. But we know for that to happen, we must have N1 being larger than N2. So the first medium must have a larger than or equal to refractive index than the second material. So like this. But in our case, we have 1.33 should be larger than 1.47, but this is not true because, well, yeah, 1.47 is larger than 1.43. So if the ray would be coming from the other way, then total internal reflection would be possible, but in this case, unfortunately, it is not possible whatsoever. And in part B, then, we are asked to calculate the angle of incidence at the air-plastic interface. So we want to, so this is air, this is the plastic, and we want to find this angle of incidence. And well, we know pretty much everything here. We know that the refractive index of air is just 1. You should know this, I think, but this is also listed up here. They usually always give these values, you don't need to remember them. But so this is n equals 1, and we just need to simply apply Snell's law, where this is the first medium, this is the second medium, and we are given the angle of refraction of being 32 degrees. So we can just simply write up the equation that n air over n plastic is equal to the angle in the plastic divided by the angle in the air. Again, remember this is always between the ray and the normal of the plane. So if we want to find the incident angle, that's going to be in the first material, there's going to be sine of theta 1, and this will just be n plastic over n air times the sine of theta 2. And then if we take the arc sine of all of this and plug in all the values, we will see that this is the arc sine of 1.6 over 1 times the sine of 32 degrees, which will give us 57.98 degrees. Yes. And then in part C, we are actually asked to calculate a critical angle for the plastic water interface. So we see plastic is here, water is here. So we need to calculate this angle over here. We need some critical angle over here. So as we have discussed over here, the critical angle can be simply calculated with this formula here, as we derived it in the previous question. And yes, so this should be critical angle theta c. So if we just apply this formula, then we will see that this is just the arc sine of, let's see what the materials are. So N2 is going to be 1.33, N1 is going to be 1.66, as those are the first and second materials. And as you can see here, we're going to have a number smaller than 1. So this is indeed possible here. And our calculator will give us that this angle is approximately 56 degrees. Now, you probably want to write down some of this simplification that I did here, saying that this sine has to be 90 as yeah, or if you maybe referred to this already in part A2, then you can say that you calculated this in A2 and just apply the formula here. And the next question is about polarization. This is not part of the new syllabus anymore starting in 2025, so no need to go over this anymore. But just as an interesting fact, what is meant by polarization is that light is pretty much made of perpendicular electric and magnetic waves. So we have some waves like this, electric waves, and then perpendicular to them we have magnetic waves. And if we polarize this light, what it means that light usually oscillates in every direction like this. We have these planes of oscillation, and if we polarize it, what that just means is that we remove some of these oscillation planes, and so we reduce the intensity of the light. And yeah, but again, this is not part of the syllabus anymore. We don't need to study it anymore. Part E is also in the old syllabus, so this is not going to be part of the new examination anymore. Neither is F or part 2. And so that was question 2 in the 2023 paper 2, and see you in the next one.